Preparing for a technical interviews at Oracle India interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you find the first non-repeating character in a string? I would solve this in 2 passes. First, I store each character's frequency in a HashMap. Second, I scan the string from left to right and return the first character whose count is 1. This preserves the required order and runs in O, N, time with O, K, space, where K is the character set size. I would explicitly handle an empty string and return a suitable sentinel when every character repeats. While answering, explain frequency counting, order preservation, HashMap complexity, character encoding assumptions, edge cases involving empty strings, and why a 2-pass solution is clearer than repeated scanning. Question 2. What is the difference between an interface and an abstract class in Java? An interface defines a contract, while an abstract class can provide shared state and partial implementation. A Java class can implement multiple interfaces but extend only one class. I use interfaces for interchangeable capabilities, such as storage providers, and abstract classes when subclasses share fields or lifecycle logic. Modern interfaces may contain default and static methods, but constructors and instance state still belong to classes. The decision should follow reuse versus behavioral flexibility. Make sure to cover inheritance limits, constructors, state, default and static methods, access modifiers, multiple interface implementation, abstraction intent, and practical examples from Oracle-style enterprise applications. Question 3. How does HashMap work internally in Java, and what happens during collisions? HashMap computes a key hash, maps it to a bucket, and uses equals to locate the exact entry. Collisions are handled through linked nodes, and heavily populated buckets can become balanced trees in modern Java implementations. When size exceeds the load factor threshold, the table resizes. Average lookup is O, 1, though poor hashing can degrade performance. I also emphasize immutable keys and consistent hashcode in equals implementations. In your answer, discuss hashing, bucket indexing, equals and hashcode contracts, collision handling, resizing, load factor, treeification, mutable keys, and expected versus worst case complexity. Question 4. How would you detect a cycle in a linked list without using extra space? I would use Floyd's algorithm with a slow pointer moving 1 step and a fast pointer moving 2. If the fast pointer reaches null, the list is acyclic. If both pointers meet, a cycle exists. To find its entry, I reset one pointer to the head and move both 1 step at a time. Their next meeting point is the entry. This uses O, 1, space and O, N, time. Be sure to mention Floyd's tortoise and hare algorithm, pointer movement, meeting point proof intuition, null termination, complexity, and how to locate the cycle's starting node afterward. Question 5. How would you design an LRU cache with O, 1, get and put operations? I combine a HashMap for direct lookup with a doubly linked list ordered from most recently used to least recently used. A get removes the node and moves it to the front. A put updates an existing node or inserts a new one at the front. If capacity is exceeded, I remove the tail and its map entry. Both operations are O, 1. In production, I would define thread safety requirements explicitly. Focus on combining a HashMap with a doubly linked list, recency updates, eviction behavior, capacity handling, synchronization considerations, and complexity of every operation. Question 6. Explain database normalization and when you might deliberately denormalize a schema. Normalization organizes data to reduce redundancy and anomalies. For example, customer information should not be duplicated across every order row. Third normal form generally separates attributes that depend on non-key attributes. I denormalize only when measured read performance or reporting needs justify duplication, such as storing an order total. Then I define ownership, update rules, and reconciliation processes, because denormalization improves reads but increases storage and consistency complexity. Cover first, second, and third normal forms at a practical level, update anomalies, functional dependencies, joins, read performance, consistency costs, and evidence-based denormalization decisions. Question 7. What is the difference between clustered and non-clustered indexes? A clustered index determines how table rows are physically organized, so a table typically has only one. A non-clustered index is a separate structure containing indexed values and row references, allowing multiple indexes. Clustered indexes are strong for range scans, while non-clustered indexes accelerate selective lookups but may require a second fetch. Every index consumes storage and slows writes, so I choose them from execution plans and workload measurements. In your answer, explain physical row ordering, secondary index structure, lookup cost, range queries, uniqueness, write overhead, storage, and why index selection must reflect actual query patterns. Question 8. How do database transactions achieve ACID properties? Atomicity means all operations commit or roll back together, consistency preserves constraints, isolation controls concurrent visibility, durability preserves committed data after failure. Databases implement these with transaction logs, locking or MVCC, checkpoints, and constraint enforcement. I keep transactions short and place only related changes inside them. Isolation should match business needs. Stronger levels reduce anomalies but can reduce concurrency. Understanding the database's exact guarantees matters more than memorizing labels. Make sure to define atomicity, consistency, isolation, and durability, then connect them to logging, locks, MVCC, commit protocols, constraints, failure recovery, and practical transaction boundaries. Question 9. What causes deadlocks, and how would you prevent or resolve them? A deadlock occurs when competing transactions or threads hold resources while waiting for one another, creating a cycle. I prevent it by acquiring locks in a consistent global order, keeping critical sections short, avoiding unnecessary locks, and using timeouts. Databases can detect cycles and abort one transaction. Applications should retry safely with bounded backoff when operations are idempotent. Thread dumps and database deadlock reports help identify the exact dependency chain. Discuss mutual exclusion, hold and wait, no preemption, circular wait, lock ordering, timeouts, detection graphs, transaction scope, retries, and diagnosing deadlocks from database or thread dumps. Question 10. How would you design a scalable URL shortening service? I would expose create and redirect APIs, storing a short key mapped to the original URL and metadata. A distributed ID generator or encoded sequence prevents collisions. Redirects are read-heavy, so I would place a cache before replicated storage and use expiration policies. The service should validate URLs, rate limit abuse, and support analytics asynchronously. For availability, temporary stale mappings are usually acceptable, but creation requires durable, unique writes. Cover API design, unique key generation, persistence, redirects, caching, expiration, collision handling, read-heavy traffic, replication, rate limiting, and availability versus consistency trade-offs. Question 11. What is the difference between processes and threads, and when would you choose each? Processes have separate address spaces, offering stronger isolation but requiring heavier communication mechanisms. Threads share a process's memory, making communication faster but introducing synchronization and failure risks. I choose processes when security or fault isolation matters, and threads for related tasks that benefit from shared memory. In Java, I generally use managed executors rather than creating raw threads, bound pool sizes, and distinguish CPU-bound work from blocking I/O. Be sure to compare memory isolation, communication cost, scheduling, failure containment, shared state risks, context switching, CPU-bound versus I/O-bound workloads, and Java executor usage. Question 12. Explain virtual memory and page faults. Virtual memory gives each process an isolated address space while the operating system maps virtual pages to physical frames. The TLB caches translations, and a page fault occurs when a needed page is absent or permissions fail. The operating system may load it from disk, which is dramatically slower than RAM. Excessive faults cause thrashing, so I monitor memory pressure, improve locality, and avoid uncontrolled process or cache growth. In your answer, cover virtual to physical address translation, pages, page tables, TLBs, demand paging, disk latency, thrashing, and how working set behavior affects application performance. Question 13. How would you investigate a Java application with unexpectedly high memory usage? I first establish whether the growth is Java heap, metaspace, native memory, threads, or direct buffers. I review garbage collection logs and metrics, then capture a heap dump near the problem point. A dominator tree can reveal collections retaining unexpected objects, such as unbounded caches or listeners. I reproduce under representative load, fix ownership or eviction, and verify after deployment. Increasing heap size may hide symptoms but does not solve a leak. Focus on distinguishing heap, native memory, and leaks. Mention garbage collection logs, heap dumps, profilers, retained objects, allocation rates, container limits, and reproducible diagnostics. Question 14. What is the difference between checked and unchecked exceptions in Java? Checked exceptions must be caught or declared, so they communicate conditions callers may reasonably recover from, such as a missing file. Unchecked exceptions extend runtime exception and commonly represent programming errors or invalid arguments. I avoid catching exceptions merely to silence the compiler. I handle failures at the layer that can recover, preserve the cause when wrapping, and design APIs consistently. Excessive checked exceptions can clutter interfaces and encourage poor handling. Mention compiler enforcement, recoverable versus programming failures, runtime exception, API design, meaningful handling, exception wrapping, logging, and why excessive checked exceptions can harm maintainability. Question 15. How would you make a REST API reliable and backward compatible? I start with stable resource names, correct HTTP methods, explicit status codes, validation errors, and documented schemas. Put should be idempotent, while non-idempotent creation can use an idempotency key. I add pagination, timeouts, authentication, correlation IDs, metrics, and structured logs. Backward compatibility means additive changes, tolerant readers, and contract tests. Breaking changes require versioning and a migration plan. Retries must use bounded backoff and avoid duplicate side effects. Cover resource-oriented endpoints, HTTP semantics, validation, idempotency, status codes, versioning, pagination, timeouts, retries, observability, authentication, and contract testing. Question 16. How do you decide between synchronous calls and asynchronous messaging in a distributed system? I use synchronous calls when the caller needs an immediate result and the dependency is reliable enough for the latency budget. I use asynchronous messaging for long-running work, traffic smoothing, decoupling, and reliable event propagation. Messaging introduces eventual consistency, duplicate delivery, ordering challenges, and operational overhead. Consumers must be idempotent, acknowledge safely, retry transient failures, and route poison messages to a dead letter queue. The choice follows business latency and consistency requirements. Discuss latency, coupling, reliability, backpressure, delivery semantics, ordering, retries, dead letter queues, idempotency, user experience, and operational complexity. Question 17. What is a race condition, and how would you fix one in Java? A race condition occurs when outcome depends on timing between concurrent operations. For example, incrementing a shared counter is not atomic because read, modify, and write can interleave. I would use atomic integer for a simple counter, synchronized or a lock for compound invariants, and concurrent collections for shared maps. Volatile provides visibility but not compound operation atomicity. I also reduce shared mutable state and test with stress and concurrency focused tools. Be sure to explain unsynchronized shared state, lost updates, atomicity, visibility, synchronized blocks, volatile limitations, locks, atomic classes, concurrent collections, and minimizing critical sections. Question 18. How would you optimize a slow SQL query in an Oracle database? I reproduce the query with representative data and inspect its execution plan, actual row counts, join methods, and access paths. I check statistics, predicate selectivity, unnecessary columns, functions on indexed fields, and inefficient pagination. Appropriate composite or covering indexes may help, but indexes also increase write cost. I validate changes with realistic benchmarks and monitor production impact. Hints are a last resort because they can become brittle as data distribution changes. Mention execution plans, indexes, cardinality estimates, joins, predicate selectivity, statistics, full scans, bind variables, partitioning, pagination, and measuring before changing production queries. Question 19. How would you test a payment or order processing service? I begin with unit tests for validation, pricing, and state transitions, then integration tests against realistic database behavior. Contract tests protect communication with payment providers, while a small number of end-to-end tests verify critical journeys. I test retries, timeouts, duplicate requests, partial failures, concurrent updates, and reconciliation. External systems should use controlled fakes or sandboxes. Every test should assert durable state, omitted events, audit records, and useful diagnostics. Cover unit, integration, contract, end-to-end, failure injection, ID impotency, concurrency, security, data consistency, observability, test isolation, and realistic external service behavior. Question 20. Tell me about a technically difficult project and how you made engineering trade-offs. In one project, an order service became slow during peak traffic because every request performed several synchronous database calls. I measured latency, identified the dominant queries, added targeted indexes, cached stable reference data, and moved reporting work to an asynchronous pipeline. I partnered with operations to add dashboards and rollback safeguards. P95 latency dropped substantially while correctness remained intact. The key trade-off was accepting eventual consistency for reports, not for order confirmation. In your answer, use a clear situation task-action result structure, quantify impact, explain alternatives, mention collaboration and ownership, and connect decisions to reliability, performance, maintainability, or customer value. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.